So in this video I'm going to discuss the idea of conservation of momentum. So we've already looked at conservation of energy, and that energy can be neither created nor destroyed. It can only change forms. And we're dealing in this unit only with mechanical energy. So there can be some loss of energy to some other form that we're not equating, like thermal energy or sound or something like that. But when we look at the idea of conservation of momentum, momentum is always, no matter what, conserved, right? So there will never be a loss in momentum, right? So let's first take a look at the idea of explosions. And then in later videos, I'll talk about when things collide or run into each other. So essentially an explosion is defined as when we start with some object that has some mass, right? So let's just say that it's a bomb or something that's a 10 kilogram mass, right? And when it explodes, these pieces of it are going to fly, off in every direction out from this source. So at the beginning, before the explosion, if we were to calculate the momentum, so beginning, we have a mass. We want to do momentum is mv, so mass, which is 10, and the object is not moving, so the velocity is 0, so the momentum is actually 0, kilograms times meters per second. Right? So how can momentum be conserved in this situation where at the beginning you have something that's not moving, and then at the end you have all these things that are moving? And the reason is because momentum is a vector, because it's based on velocity, which is a vector. So if we were to calculate the momentums of all of these different objects radiating out, we would end up with a net momentum of 0. Right? So this vector would cancel this vector, and this one, and this one, and this one, and these. Alright, so let me kind of give you an example where we can actually quantify it that's a little bit simpler. So let's say we have two people, and they're standing on roller skates, and one person is, I'll just roughly draw this. This is going to be rough. Here's the roller skates, right? And we'll say that this person is 40 kilograms, right? And then you have a friend here, also on roller skates, that has a mass of, say, 55 kilograms, right? If they were to initially, if they're just standing there and they're not moving at all, their velocities are 0, so the momentum in this case before would be 0 kilograms times meters per second, right? Then let's say that they push off from one another, and so this person flies left, and this person, to the right, and this person flies to the left in opposite directions. And we'll say the 55 kilogram person has a velocity of 2.5 meters per second. Could we figure out this person's velocity given a conservation of momentum? Alright, so our equation would be that the momentum at the beginning, so momentum before the explosion, so before, must be equal to P after. Right? So this is the idea that we're going to use with all of our collisions and explosion equations from here on out. What's involved in the situation before, and we calculate. What's involved in the situation after, and we calculate, and we set them equal to one another. So before, we're going to have that momentum of 0, and then afterwards, we have the momentum of person, we'll call this person A, and we have to call this person B, right? So we have the momentum person A, so mass times their velocity, plus the momentum of person B. So we just have there two momentums. And the reason this is going to work is because velocity is a vector, right? So we set 0 is equal to 40 times V plus the mass of this person, which would be 55 times 2.5. Right? So if I just calculate that out, we'll get 137.5. And again, we're going to subtract this over here. So we'll have a negative 137.5 is equal to 40 v. So just divide by 40. So the velocity of the this kid is going to be 3.43. So the velocity is negative 3.44 roughly meters per second. Right? So this makes sense that this is negative, right? Because it's going to the left. And also, if we look at the idea of, just using our common sense, or if you've already done part of the car lab, when something moves off in this direction, if it has a bigger mass, it's going to have a slower relative velocity. So over here, if you have a smaller mass, you would have a larger relative velocity. Right? So that is conservation of momentum in explosions.